Maria Teresa Malheiro from Universidade de Minho, who will talk about model spaces and Toeplitz kernels. Welcome.
Thank you very much. I would like to thank to the organizers for giving me the opportunity of giving this talk and to participate in this big and very good event. I want to congratulate you for the quality of this focus program. I will talk about model spaces and kernels of Toeplitz operators. Model spaces are a particular type of kernels of Toeplitz operators. These kernels of Toeplitz operators, are usually called Toeplitz kernels or even T-kernels. The properties of these kernels are more fully understood than those of the model spaces. So we shall take advantage of this knowledge to better understand the properties of model spaces. In this talk, we will see that knowing some particular elements of a T-kernel, we may say something about the dimension of the T-kernel. And we will define and characterize maximal functions of a Toeplitz kernel and in particular of a model space. We also going to deduce some properties of model spaces using maximal functions. At last, we will see some relations between kernels of Toeplitz operators when the symbol of the Toeplitz operator is an inner function. But first, I have to introduce some notation. I will work in the context of the RD space in the upper and lower half plane for p greater than 1. HP plus is the Banach space of analytic functions in the upper half plane such that it satisfies this condition. And HP minus is the Banach space of analytic functions in the lower half plane such that it satisfies this condition. These spaces are usually identified with subspaces of the Lebesgue space LP. We will also use the algebra H infinity plus and minus as the space of bounded analytic functions in the upper and lower half plane respectively. I will also define here the Smirnov class is the subalgebra of the holomorphic functions in the upper half plane, and these functions of the Smirnov class are quotient of functions that are both in the union of the HP plus functions such that the denominator is outer. I will use this notation for the inner and outer factorization of HP plus or minus function. I plus or minus will be an inner function in H infinity plus and minus, and O plus minus will represent an outer function in HP plus or minus. Toeplitz operator with a bounded symbol is an operator which is defined in HP plus in this way. We multiply the function, the HP plus function f by the bounded symbol G, and we obtain an LP function, and then we use the projection of LP onto HP plus parallel to HP minus, and we obtain again an HP plus function. And then we define the kernel of the Toeplitz operator. The kernel of the Toeplitz operator is a subspace of HP plus functions such that they satisfy this equation. But due to the definition of the Toeplitz operator, in this case, in the context of the upper and lower half plane, solving this equation is equivalent to solve this Riemann-Hilbert problem. I present here some properties that we will need and we will use along the presentation. If we have an invertible bounded analytic function in the upper half plane, multiplying the elements of a kernel of a Toeplitz operator by H plus, we obtain another kernel, this time with this symbol. We can read this property, this relation, as saying that H plus is a multiplier of this kernel onto this kernel here. If H minus is bounded and analytic and invertible in the lower half plane, we have that these two kernels coincide. From these two properties here, we can write the following, that the kernel of a Toeplitz operator whose symbol is of this form is equal to this space of functions. So if we may factorize a symbol of a Toeplitz operator in this way, it is possible to reduce the study of a kernel of a Toeplitz operator of this form to the study of a kernel, of a T-kernel whose symbol is of this form. We also have, we will use this often along the presentation, if the kernel of the Toeplitz operator is non-trivial, and if we multiply the symbol of the Toeplitz operator by an inner function theta, then this kernel is strictly included in this kernel. And in the same way, this property here, this inclusion here, is equivalent to this inclusion in this side. If we substitute in this case, if we, for example, if we consider the inner function of this form, a k power, a positive k power of the rational function xi minus I over xi plus I, we have this inclusion here. And from this, we may say that if a kernel of a Toeplitz operator is finite dimensional, then if we multiply the symbol by a rational function of this form, we have that this kernel is also finite dimensional. And it is also possible to prove that if the kernel of a Toeplitz operator is infinite dimensional, then the kernel of the Toeplitz operator with this symbol is also infinite dimensional. Here is a sketch of the proof for the case where k is equal to 1. So we may say that these two Toeplitz kernels are simultaneously finite or infinite dimensional. We will use this, but we will return to this relation later in our talk. Now we will see that knowing some particular elements of a Toeplitz operator, we may say something about its dimension. First, we know that for every HP plus function, there is a T-kernel containing the span of that function. For instance, if we consider the inner and outer factorization of the HP plus function, and if we construct the symbol as the complex conjugate of phi plus divided by the outer factor, we have that G phi plus is equal to, we have here the complex conjugate divided by O plus times high plus Ho plus. This cut with this. High plus is the inner function, and then this is equal to the complex conjugate of O plus. As O plus is an HP plus function, so the complex conjugate is an HP minus function, proving that phi plus belongs to the kernel of TG. And if we know that a function of this form belongs to a certain T-kernel, namely, for instance, Psi plus is an HP plus function, and P1 and P2 are polynomials, such that the degree of P1 is less or equal than the degree of P2, and all the zeros of P2 are all in the lower half plane, we may say that the dimension of the kernel is at least equal to the number of zeros of the denominator minus the number of zeros of the numerator in the lower half plane plus 1. For example, if we have a function of this form, a simple example, just to illustrate this, Psi plus, considering Psi plus an HP plus function, we have that every T-kernel that contains a function of this form, its dimension, every T-kernel that contains its dimension is at least equal to 3. So this raises the question, is there something which in a finite dimensional setting would correspond to a smallest possible dimension for all T-kernels containing Phi plus? And the answer is yes, there is. There is the concept of minimal T-kernel of a HP plus function, which is denoted in this form and means that every kernel which contains Phi plus also contains this T-kernel. And the minimal T-kernel is the kernel of the Toeplitz operator whose symbol is of this form. We have already proven, we have already seen that Phi plus belongs to this kernel. Now we have to prove that for every T-kernel that contains Phi plus, then that T-kernel also contains this T-kernel. Considering this T-kernel with H as a symbol, an L-infinitive function, and be such that Phi plus, our function, belongs to this kernel. If this belongs to this kernel, this means that H times Phi plus is an HP minus function. And from this, we can take that the symbol can be written in this form, in this green form. Now we have to prove that this kernel is contained in this kernel. We are going to prove in the following way. We pick an element of this T-kernel, which means that this product is an HP minus function, and we have to prove that H Psi plus is also an HP minus function. Due to the form of H, this is equal to this function over here, and this can be written in the following form as this function. This blue part is equal to a Psi minus function, so we have that H Psi plus is equal to this function over here, to the quotient of these two functions. This function belongs to LP, as H is an L-infinite function, Psi plus is an HP plus function, so we have that this belongs to LP, as well as its complex conjugate also belongs to LP. And the complex conjugate of this function is in the Smirnov class. The two functions, the numerator and denominator, are both in the union of all HP plus functions, and the denominator is an outer factor. So using a theorem of Duran that says that the intersection of LP and of the Smirnov class is the HP plus set space, we have that this function is in HP plus, as the complex conjugate is in HP minus, proving that Psi plus belongs to the kernel of TH. So we have seen this in the perspective of an HP plus function. We have an HP plus function, and we looked for a minimal t-kernel. But we may see this in the perspective of the t-kernel. We have a t-kernel, and we say that an HP plus function is a maximal function for the t-kernel if the t-kernel is the minimal kernel of phi plus. Sørensen, in a paper of 1992, proved in a lemma, established in a lemma, that every t-kernel is the kernel of a Toeplitz operator with a symbol of this form. In the context of the disk, but proving that every t-kernel is the kernel of a Toeplitz operator with a symbol of this form, where O is theta is an inner function and F is an outer function. So Kammerer and Partington, using this lemma and from the theorem that we have seen previously, prove that every t-kernel is a minimal t-kernel. Saying in another way, every t-kernel contains maximal functions. These results lead us to say that if we have two t-kernels satisfying this condition, if we have one t-kernel contained in another t-kernel, this is equivalent to say that every maximal function of every maximal function of the kernel of Tg is contained in the kernel of Th. And we may generalize this. We may generalize this if we consider an holomorphic function W. We may prove that this space is contained in this space if for a maximal function of the kernel of Tg, W times phi plus is in the kernel of Th. And so we have the following theorem. We have that if we have two t-kernels non-trivial, and considering an holomorphic function defined in the upper half plane, we have that this condition is valid if and only if these two conditions are valid. These two conditions are obviously necessary, so we only have to prove that they are sufficient conditions. So let us pick a maximal function of the kernel of Tg, meaning that the symbol can be written in this form using the inner and outer factorization of the maximal function, and such that W phi plus is in the kernel of Th. The proof of this theorem, as I said before, is similar to the proof of the previous theorem. But now because of the fact that W phi plus is in the kernel of Th, we see that HW phi plus is equal to an HP minus function, meaning that we may write HW as this green function. And then we have C plus. We want to prove that for any function in the kernel of Tg, meaning that we have this relation here in blue due to the form of G, and the form of the symbol comes from the fact that the kernel of Tg is the minimal kernel of phi plus. We now want to prove that W phi plus is in the kernel of H. So we have to prove that this is an HP minus function. And we prove this in the same way as before. This is equal to this function, can be written in this form. this is equal to an HP minus function, and we obtain a quotient of two functions of this form. And as we have seen before, this belongs to the complex conjugate of the Smirnov class, and simultaneously it is on LP because of our hypothesis that W multiplied by the kernel of TG is in LP. So we have that this function is in HP minus, meaning that WC plus is in the kernel of TH. Now we are going to characterize all maximal functions of the T kernel. If we have a non-zero symbol such that the kernel of the Toeplitz operator is non-trivial, we may define G is different from 0 almost everywhere in the real line. So we may talk about the inverse of G. And phi plus is the maximum function of a Toeplitz kernel if and only if phi plus is an HP plus function, such that it can be written in this form as the inverse of the symbol times an outer factor in HP minus. Let us prove that this condition is necessary, assuming that phi plus is a function of the kernel of TG. This means that G phi plus is a phi minus function. So we may write phi plus as the inverse of G times phi minus. And suppose that phi minus admits an inner outer factorization. So from this form of phi plus, we may write phi plus in this form. And if we multiply both sides of this equality by the complex conjugate of I minus, we have that phi plus, this is still an HP minus function, and we have that phi plus belongs to the kernel of a Toeplitz operator whose symbol is this function now. But we have seen in the first slides that this kernel is strictly included in the kernel of TG. So this contradicts the fact that the kernel of TG is the minimal kernel of phi plus, if we assume that phi minus is not outer. Now, to prove that it is a sufficient condition, we have use the same arguments as before. Let's consider phi plus an HP plus function such that phi plus is a function of this form with O minus outer. And then we are going to prove that phi plus is a maximal function of TG. If phi plus belongs to a G kernel with a symbol H, this means that it satisfies an equality of this form. And from the form, by the way, we may write phi plus equal to this. This establish a relation between these two symbols, H and G. Now, to show that the kernel of TG is a minimal kernel, we pick a function of the kernel of TG. C plus may be written in this form, and we want to prove now that C plus is in the kernel of TH. So we have to prove that HC plus is in HP minus. And we show in analogous way as we have seen before. HC plus is in LP, and at the same time, because of the form of H and because of the form of C plus, this is equal to the quotient of two functions and this quotient is in the complex, is a complex conjugate function of a Smirnov class function. So because it is simultaneously here And here we have that this is an HP minus function. Let us see two examples. For instance, let us consider first a function that is an inner function times this function, which is outer in HP plus. From here, it is we construct the minimal kernel of C plus. Remember that to build the minimal kernel, we construct the symbol as the conjugate of C plus, the complex conjugate of the function divided by the outer factor, and so we obtain a symbol of this form. And we see that the maximal function can be written as the inverse of the symbol times an outer factor in HP minus. Another example, this function over here, where beta satisfies these two inequalities. This inequality guarantees the fact that this function belongs to HP plus, and it is an outer factor in an outer function in HP plus. We construct the minimal kernel that contains C plus, obtaining this symbol. We consider for this symbol, for this function, we consider a branch whose branch cut is from this point to the infinite and from this point to minus infinite. So this with this symbol. So from this, we have that this is a maximal function of the kernel of TG and can be written as the inverse of G times an outer factor now in HP minus. And it is also possible to prove, due to this inequality, it is possible to prove that the kernel of TG is one-dimensional. That is a thing, sorry. That is a thing that we are going to see. With maximal functions, we may have an equivalent condition to have a finite dimensional T-kernel. A T-kernel is finite dimensional if and only if their maximal functions are in this form, have an inner-outer factorization of this form, where the inner factor is rational and the outer factor is such that the kernel of the Toeplitz operator with this symbol is finite dimensional. Let us prove that these two conditions are necessary. If the kernel of this Toeplitz operator is infinite dimensional, because of this relation that we have seen before, this is remember, this is the complex conjugate of an inner function in HP plus. And because of this relation, this kernel is strictly included in this kernel, and this one, the smaller one, is infinite dimensional. So our minimal kernel is also infinite dimensional. If now let us consider that the inner function is non-rational. If the inner function is non-rational, for every function that belongs to this space, this means for every h infinity plus function which is simultaneously a product, a multiple of the inner function times an h infinity minus function, we have that alpha plus times O plus belongs to our minimal kernel. But this space is infinite dimensional because our inner function is non-rational. So this space is infinite dimensional. And if we have an infinite dimensional space contained in our minimal kernel, we have that our minimal kernel is infinite dimensional. To prove that these two conditions are sufficient to have a finite dimensional T-kernel, we only have to prove, to say that if we know that if our inner function is rational, then these two kernels are simultaneously finite or infinite dimension. We have seen this in the first slides for example, our inner function equal to xi minus I over xi plus I up to a positive power of this rational function. Okay, an example. Let us consider a symbol, an L infinite function, such that it admits a factorization of this form, which is called a bounded factorization, where G minus as well as its inverse is bounded and analytic in the lower half plane, and such that G plus as well as its inverse is analytic and bounded in the upper half plane. In this case, it is possible to characterize the kernel of the Toeplitz operator. In this case, the kernel of the Toeplitz operator is of this form, where this polynomial has degree less or equal than k minus 1. And the dimension of the kernel is equal to k. So we have a finite dimension kernel. And for example, this function is a maximal function of the kernel, where the inner factor is a rational function and the outer factor is such that the kernel of the Toeplitz operator, whose symbol is the complex conjugate of the outer factor divided by the outer factor, is one-dimensional, and it is finite dimensional, as we have proven before. And now let us go to the particular case of model spaces. As we have seen, model spaces can be defined in this way as the intersection of HP plus function and multiples of theta times HP minus function. Considering this definition for model spaces, we have that model spaces are particular types of kernels of Toeplitz operator whose symbol is the complex conjugate of theta. And we have characterized the maximal functions of T kernels. The maximal functions of T kernels could be written in this form as the inverse of the symbol times an outer factor in HP minus. And now this is simpler in the case of a model space. In the case of a model space, we have that maximal functions are of the form theta times an outer factor in HP minus. For example, if theta is a Blaschke product, and considering a zero of the Blaschke product, a maximal function can be written as theta times a rational times an outer factor in HP minus. If theta can be factorized in this form, where the factors are invertible and bounded in the respective half planes, and B is a Blaschke product, we may see that a maximal function is a function of this form, where we have here theta, and this is an outer factor in HP minus. And this is relevant, this case over here, because we have that for any inner function can be factorized in this way using a Blaschke product and H infinite and analytic and bounded functions in the lower half plane, and analytic and bounded functions in the upper half plane. Notice that from here we may write theta, may represent theta using the maximal function. Theta can be written as g minus times this polynomial times our maximal function. So we may write theta using the maximal function. And now we will deduce a well-known property using maximal functions. We know that this condition is equivalent to have this, that a model space is contained in another model space if and only if θ2 divides θ1 by an inner function. If θ1, and this could be proven by using maximal functions. If θ1 is equal to θ2 times another inner function, we have that this kernel is contained in this kernel. And this is our model space K θ2, and this is our model space K θ1. And now to prove that if this condition is true, then we have a relationship between θ1 and θ2 in this way. We use the fact that if we have a maximal function of K θ2, this maximal function is equal to θ2 times an outer function in HP minus. And as we have this relation between the two model spaces, we may write the complex conjugate of θ1 multiplied by phi plus, we obtain a psi minus function. Using the form of phi plus, we have this relation here. And if we use the inner and outer factorization of psi minus, we have this relation over here. And if we multiply both sides by the complex conjugate of θ2, we obtain this relation here. And from the uniqueness of the inner and outer factorization, we have that this part inner is equal to this part inner. So θ1 is a multiple of θ2 times the complex conjugate of I minus, which is an inner function. This is a well-known, as we have seen, this is a well-known property that can be proven using, for example, maximal functions. We also have that having a maximal function of a certain model space and multiplying that maximal function by theta, this is also a maximal function of another model space, of this model space K, whose symbol is θ1. And independently of this result, this model space can be written as the direct sum of a model space and this space over here. And as we have seen before, theta, any inner function, can be written in this form using the maximal function. So a model space can be written as the direct sum of a model space and this space using the maximal function. We also have that if two model spaces are related in this way by an invertible and bounded function in the upper half plane, then we may say that psi plus is a maximal function of K θ2 if and only if psi plus multiplied by H plus is also a maximal function of K θ1. And if we pick a finite set of maximal functions that are maximal functions of each one maximal function of a finite set of model spaces, we have that there exists a minimal kernel containing this set of maximal functions. And that minimal kernel is also a model space. And the symbol of that model space, if we may call the inner function associated to that model space, is the least common multiple of all the theta, of all the inner functions associated to k theta I. And this model space is the closure in HP plus of the sum of these model spaces. And finally, we have the following. When we have two kernels or two T kernels whose symbol only differ by an inner function, we know that this kernel is strictly contained in this kernel, if theta is not constant. But we may ask how smaller, how the dimensions of both are related. We may consider 4 situations: if theta is a finite, or if theta is not a finite Blaschke product. If theta is finite and the kernel in our T kernel is also finite dimensional, then we have that the dimension of the kernel, of the T kernel with symbol theta G, is equal to the maximum between 0 and the difference between the dimension of the kernel and the number of zeros of theta. If the number of zeros of theta is greater than the dimension of the kernel of Tg, then theta annihilates this T kernel, meaning that the dimension is equal to 0. The kernel will be trivial. If the kernel is infinite dimensional and theta is finite, for example, just to better visualize the example, if, for example, theta is r power to a positive power, we have that the kernel of Tg can be written as the direct sum of these two spaces, of this kernel and of this space. Of course, here we may not say which is the dimension of the, both are infinite dimensionals, this kernel and this kernel over here. But look that this kernel is a direct sum of these two spaces, and this space over here as dimensional equal to k, as a finite dimensional. And if theta is not a finite Blaschke product, we have that if the dimension of the kernel of Tg is finite, then theta annihilates the kernel, meaning that the dimension will be equal to 0. And if are both infinity, we may have several situations. Okay, we may have finite or infinite dimension. And I will stop here. Thank you very much for listening to me. Thank you.
Thank you very much. Let's thank the speaker. Any questions, comments?
Is there any nice voice model term here?
Sorry, I didn't understand.
Is there any term like nice term here? Means given a contraction with certain condition can be identified with certain kind of operators in the model space.
Sorry, could you write on the chat? Because some problems on the connection, I don't hear very well. I didn't understand very well the question. Is it possible to write it?
Okay, while question has been written, any other questions? So again, as usual, you can write it in the chat or shout it out. Okay, let's wait for the question to appear in the chat. Oh, so the question is, given a contraction on the Hilbert space with some condition, does there exist a universal operator on model space?
Given a contraction with some condition, does there exist an universal? I don't know the answer to this question. I don't know. I have not think about it.
Thank you. Okay. If there are no more questions, let's thank Maria Teresa again.
Thank you.
And we have some time